Mr. White here, me.
And Mr. Rops.
We're going to talk to you today about kinematics, which is, what is kinematics?
It's all about motion and moving and velocity, acceleration, and position or distance.
So our example today is this little dog. We should name our dog, of course. What's our dog's name, Mr. Rops?
Oh, I like the name Rover for a dog, of course.
There we go.
Woof.
Okay, so let's start with a little bit of background, some things that you should know already. If we have a position graph, so in our case, we'll say that Rover's running in meters, and our time is in seconds. So we'll just put seconds here. If we find the slope, and we know slope from 8th and 9th grade, if we find the slope of a meters and a seconds graph, we go rise, meters, over seconds, which is the run, so rise over run. And then if we find the slope of that, we have rise, which is this, over run again, which is this, and that's meters per second squared.
So that's the slope of the slope?
Slope of the slope, correct. Yeah, okay, so then we usually say that the position graph is named x of t, and then we have the meters per second graph, which is velocity, v of t, and then the meters per second squared graph is a of t, which is acceleration. That's probably old news. So,
right.
But this is a little bit of explanation where those things come from. All right. So let's say that Rover, and we're looking at a velocity graph. So this is meters per second right here. So Rover, you can see this piece of the graph to 1 second, he's moving away. So 1 second, he moves this way.
So what happens at that point at 1 second? Something's crossing the x-axis, or the t-axis. Something must have happened.
So so something happens. This is the y. The y-axis represents speed, right? So right around here, he's moving at, what is that? What would that be?
About
1 meter
per second.
Per half a second or something.
Yep.
So right there at 1 second, he's moving at 0 meters per second. He's not moving at all. So at that instant, he stopped.
Oh.
So he goes out, and then this represents negative velocity. So he turns around and comes back.
Negative meaning the opposite direction.
Opposite direction, correct. So he goes out and he comes back. But the cool part, the interesting part about these curves is, well, it appears as though this curve is smaller than this curve. And that actually means something in calculus terms. So if we actually go back and we want to find out how far he's gone, well, we can just find the area under the curve. Well, why is that, Mr. Rops?
Well, because, if we want to find the area of the curve, I know I'm going to find areas. Meters per second is the height of that little tiny rectangles we would put in there.
The height?
The height, and the width of that rectangle would be s, seconds. If I multiply those, I end up with meters.
Back to the original position. So if I find the area from 0 to 1, that should give me how far the dog has gone in 1 second. So let's go do that. So second, I have the graph here, second calc, integral from 0 to 1. And the dog went 0.733 meters.
So when I shade underneath the curve, that area actually represents the position or the distance traveled.
0 to 1 of whatever this function is, of f prime, because it's, well, v of t, I guess. Should I write v of t?
Sure.
Keep consistent here.
Yep.
Like I should be, always. So v of t is 0.733. So the integral from 0 to 1, the area from 0 to 1 is 0.733.
And that would be meters, right?
Meters. Jeez.
He didn't go very far in that 1 meter.
No, he's a slow dog. He's old. So now we want to know what, maybe he's gone from 1 to 2.
All right.
So from 1 to 2.
But because it's underneath the curve, he has to be traveling in the opposite direction.
So yeah, it's going to be a negative answer. And if you think about it, we have positive x and negative y. When I multiply a positive times a negative, that will give me negative area. So we get second calc, integral number 7 from 1 to 2. Hopefully it gives me negative 1.2. So the negative doesn't mean anything more than just I went back.
Opposite direction.
Okay, so now let's think about this. So he went out 0.733 and he went back 1.26. So he went back further than he went out.
Oh, right, because he started at that little mark, and he's going to go back further, about 0.5 meters back further.
Right. And then, of course, we could ask you acceleration questions, and then you just find the derivative, the slope at a certain point. Maybe we should do that. Find the acceleration at I don't know, 2 seconds?
2 seconds.
Well, let's go 1.2 seconds.
Okay, 1.2 seconds, perfect.
So find the acceleration, so second calc, dy dx. So find the derivative, the acceleration, at 1.2 seconds. So right there, he's moving back this way. So the acceleration at 1.2 seconds is negative 4.26. What does that mean?
That means that he's going in the backwards direction.
So he's moving back, and he's moving back pretty fast.
Right, he's going back pretty fast. Yeah. So if we were on our graph here, how could we show that 1.2 seconds? How could we show that negative 4.26?
Well, what do you mean? Like
on our graph here kind of thing, what would be at 1.26, at negative 4.26, how is that represented?
Well, we can do something like this as the slope, or we can actually plot the point, right?
Right.
Plot the point way down here at negative 4.
Exactly.
So that helps us graph the next slope, which would be the acceleration.
Cool.
Cool. All right, so let's do an example. All right, a dog.
I hope it's Rover still.
Rover may have gotten too tired, but let's just say Rover. Rover runs along the beach with a velocity of this quadratic function. The position is 5 for t equals 2. So we know that the position, so x of 2 is 5.
Right.
Okay, so 2 seconds, he's 5 meters away. That's all it's saying. Okay, so write a polynomial expression.
Oh, that just means I'm going to find the integral of the velocity function.
The velocity. So 3t squared.
Oh, so the t cubed.
T cubed.
These are nice coefficients. Minus t squared.
Minus t squared.
Minus t.
Minus t.
Plus c.
Plus c. You do not know, you need to know that, you need to make sure it goes through 2,5. And if I leave out that plus c, I don't know, probably doesn't even go through 2,5.
Right.
So 5 equals 8 minus 4 minus 2 plus c.
Right.
So 5 equals 4, 2 plus c. So c must be 3, right?
Right. And that's a good example of where those initial boundary conditions we did last class is actually needed for some kind of purpose here.
Yeah. So x of t is t cubed minus t squared minus t plus 3. Okay, so for what value of t 0 to 3 does the dog turn around? So at what time? I should have wrote there. So let's turn this graph off.
Because we're not talking about that one. We've got a new equation now.
I have it down in here. So let's graph this function. And it's not in there.
I think you've got it turned on.
Oh, yeah. That's pretty good.
Nice.
Okay, so for what values does the dog turn around? Well, let's just drag this over. Maybe we can talk about it a little bit better. Okay, so this is the velocity curve. So this right here means the dog was running back, maybe away from the ocean or something like that.
Yep.
Right here, the dog's velocity is 0. And then right here, he's running towards the ocean or something.
So he turned around.
He turned around right there.
So if it would have stayed underneath the x-axis, he would have just stopped and then just kept going in that same direction.
Mm-hmm. So for what value does the dog turn around? Well, we need to know when v of t equals 0. So we set this guy equal to 0, and then we can solve. I think we can use our calculator for this. Let's go second calc. 0.
So the velocity function equal to 0.
Go to the right, sorry, go to the left, go to the right. It's in between those two arrows. T equals 1.
Nice.
So at t equals 1 second, the dog turns around. Find the speed of the dog at 1 second. Well, that's weird.
Speed the dog at 1 second. Didn't we just figure that out?
Yeah. V of 1 is 0. We know that already.
Yeah,
So, that's an easy question.
it is an easy one.
Find the position of the dog at 3 seconds. So the position is,
That's x of t, this position.
right, so x of 3. So I need to know, this is 1, let's just assume that this is 3 seconds out here.
Okay.
So 3 seconds. So the position is he goes away from the ocean, and then he goes towards the ocean. We should be able to cancel those things out and find out where he is at that exact moment.
Right.
Okay, so I'll just say the integral from 0 to 3.
Mm-hmm.
No, something happened.
I wasn't watching close enough what you were typing in there.
7. From 0 to 3. Oh, sorry, I need to be, this is a common mistake. This is good modeling right here.
Ah,
I need to have the actual number there. So let's go to 3.1. Okay, we'll see if it works now. It might not work still. 7, 0, 2, 3. Good, 15. Okay, so at x of 3 is 15 meters away from what?
from his starting point.
From starting point. Find the total distance traveled by the dog. Well, this is a little bit different from the last example in the sense that this is distance, and in the previous example we were canceling out. So if I go back and I grab my dog here, if I go out and back, my position is 0.
Right.
But if I actually count out and back, my total distance could be, well, a couple meters.
Right.
And
So
I
if he
go
had
out.
like a pedometer on him, he's going for a jog. How many meters did he jog in those total run?
It's like running around track. If you run around once, your position is 0, but if your distance is 400 meters. So we need to count this as positive and count that as positive.
So should we take our velocity curve and break it up into 2 parts kind of thing, or integral, and break it up into 2 parts?
So we'll just do 0 to 1. So let's write that down. We'll go 0 to 1 of v of t dt, and the absolute value of whatever this is. So if it's going to be negative, we're just going to make it positive.
Right.
Plus 1 to 3 of v of t dt.
And we know that's going to be positive already because it's above the curve,
So
above
second
the x-axis.
calc 7, 0 to 1 is -1, but we know we want 1.
Right.
So he went 1 meter. And then second calc 7, 1 to 3. 16. So we went 17 meters.
Nice.
Is that right?
Yep.
Looks good to me. There you go. There's kinematics.
Great.